where a dark matter particle comes and bumps into a standard model particle. So we would see some energy deposited to a particle that we know about. And so this is the type of thing they might look for in CMS, the LHC. This might be the type of thing they look for in gamma ray telescopes. And this might be the type of thing that they look for in something that Harry works on with the xenon dark matter searches. Okay, so let's talk about indirect detection first. So you would expect the highest flux of particles coming from dark matter annihilation, where the density of dark matter is the highest, which would be like the center of a galaxy. Okay. Now, there's a whole lot of stuff that we don't know. If a dark matter particle annihilates with another dark matter particle, what happens here? What are the final states? A whole lot of unknowns, but we can look for specific things. So maybe an electron comes out. It's not really going to tell us much because electrons are charged, and galaxies have magnetic fields, and so if you see an electron coming from there, it doesn't mean that that's where it originated, and maybe it had some weird trajectory. You can't really point back to the source if you see some high energy cosmic ray. But if they produce gamma rays or neutrinos, those things don't get deflected by magnetic fields. They point back to their source. So one of the most powerful ways that people look for dark matter with indirect detection is to look in gamma ray telescopes for hot spots of gamma rays where you might not expect them. So in the range of 10 to 1,000 GeV gamma rays, it's considered very high energy gamma rays. You can't just build a telescope with, like you would with optical photons, because when these things hit the upper atmosphere, they produce a huge leptonic shower, kilometers long. Okay. Many charged particles. So gamma ray comes in, smacks into the upper atmosphere, produces a big shower of many charged particles, many of which are moving faster than the speed of light in air. So they produce Cherenkov radiation. It's basically a shock wave in air. And that Cherenkov radiation can propagate down to the surface of the Earth, where we can image that with telescopes. So here's one such observatory. These are optical telescopes, but they look for these kind of flashes of light. This is something that might last 10 nanoseconds. It's very fast. This is in Namibia. It's called the Hess experiment. Okay. There's another one in the Canary Islands in Palma called MAGIC. Similar design. You see just a big array of mirrors. Here in the US, in Arizona, there's the Veritas experiment. Okay. So far, these are the largest scale experiments of their type, and the community has come together to work on designing the sort of ultimate phase of these, which is called the Cherenkov Telescope Array, CTA. There's going to be a lot of telescopes of many different sizes, an observatory in the northern hemisphere, an observatory in the southern hemisphere. I actually spent a few years working on developing this concept. Okay. So this is the kind of thing they might see. So this is actual data from Hess looking towards the galactic center. You see 2-point sources, you subtract those out, you see some residual emission of gamma rays, and you can place limits on dark matter with that. So they actually, because they're looking for annihilation, they actually directly probe this annihilation cross-section, which is directly related to the relative abundance. So we can draw a line here that relates to what it needs to be a weakly interacting massive particle based on that. So they're able to sort of carve out some parameter space here. They exclude regions above that. The Fermi satellite, which is a little bit lower, deals with gamma rays a little bit lower in energy, can actually reach this, but it's not like we actually rule out dark matter below this mass because they're really looking for a specific final state, BB bar. So there's no rule that dark matter, when it annihilates, has to create a bottom and anti-bottom quark. But this is the way that they look for dark matter in telescopes. Okay, so let's go back to this. Direct production. Well, this thing I drew here, standard model goes to some new particles. Actually, that's just a cartoon. That's not something you would be able to observe because these things would just leave the detector. You need a standard model in the final state, standard model particle in the final state. So something like this. This is a diagram from a recent CMS paper where they looked for dark matter. They collide a quark and an anti-quark. What comes out is perhaps some dark matter and quarks. And so the difficult thing with the Hadron Collider is that they're firing protons at each other, but it's not protons that collide. It's like a quark from one proton and a quark from another, an antiquark from one and an antiquark from another. So they actually don't know what the initial momentum is, what the momentum of the initial state is. But they do know that the component of a momentum transverse to the beam is 0. And so the final state has to have no component of momentum transverse to the beam. But if you miss part of that, if you miss half of the final state, it might look like the other half of the final state that you do detect does have some net momentum transverse to the beam. So they call this missing transverse momentum or missing transverse energy. So you search for evidence of stuff that left your detector without being detected by looking for momentum imbalances in the things that you do detect. And so there's a lot of, it's tricky with the colliders because you have to specify a lot of things about what's going on, what you're looking for, what final state you're looking for, what's the nature of the mediator particles you're looking for. I'm showing you just one example. This is for a vector mediator, CMS. They're able to exclude a region of parameter space. This is the mass of the dark matter, the cross section, the readiness it would have to interact with a proton or a neutron. They exclude these regions here. These come from exclusions of a different type that I'll talk about later. So they're not actually very competitive in this regime here, but if you look at axial vector mediation with protons, they can really beat out some of the other methods that we have. And they're also sensitive to different masses too, that some other methods are not sensitive to. So this is just introducing the last concept, which I'm going to talk about, which is direct detection. Okay, so we want something that is related to weak physics, that annihilates with a weak cross-section, to interact with a standard model particle, which means protons or neutrons. Well, protons and neutrons and electrons all participate in weak interactions. So I could get a WIMP to scatter with an atomic electron. But the problem is that this is sort of kinematically suppressed. If this is a particle that has 100 GeV in mass, and here's a particle that has half an MeV in mass, there's sort of not so much possibility for this thing to transfer too much energy to the electron. So this process is possible, but it's kinematically suppressed. On the other hand, if this particle were to scatter with the nucleus is generally around 100 GeV in mass. This is very kinematically well matched to scatter with a WIMP. Additionally, the energy of the interaction is not large enough to really probe the substructure of the nucleus. So the WIMP would scatter with the whole nucleus as a whole, and the rate for this to happen gets an enhancement of A squared. A is the number of nucleons, protons and neutrons, due to this coherence, the fact that this interaction is not probing substructure. So really, if we want to look for evidence of a WIMP interacting with normal matter, what we want to look for are an anomalous source of nuclear recoil, situations where a nucleus just goes in one direction. We don't see what caused it. So people started to do these experiments in the 80s, looking for anomalous sources of nuclear recoils. And I'm just going to show you, before I really talk more about these experiments, I want to show you a timeline of what is our sensitivity. Imagine I had a 60 GeV mass WIMP. What is the cross-section with a nucleon that we can exclude? Each dot is an experiment over time. Okay. And I'll just highlight, just for fun, I'll just highlight with stars. These are experiments that I've worked on. Okay. And here's the gap where I was working on Cherenkov, gamma ray shot. Now, we're talking about the progression of a technology with time. And if we want to talk about how technology progresses with time, there's like a gold standard for measuring how technology progresses with time. Anyone know what I'm talking about?
Moore's law.
Moore's law, exactly. Moore's law, you get a doubling of quality basically every roughly 2 years, or a factor of 10 improvement every 6.5 years. So how are we doing with respect to Moore's law? Well, we don't have a straight line like in Moore's law. We can kind of say that we have maybe 3 different epochs of progress. And if I overlay Moore's law, flip it, It turns out we're actually beating Moore's law in terms of, this is the sensitivity, what rate of WIMP interactions are we sensitive to as a function of time. It's pretty impressive. Okay, so, but I want to give you some real sense because, you probably don't have any physical intuition about what a cross-section of 10 to the minus 44 square centimeters means. Okay? Well, what it means is that if I had a particle detector whose absorber mass was 1 kilogram, something around this range, which is, these are real sensitivities, these experiments were sensitive to these rates, this 1 kilogram of detector mass would see on order of 1 event per century. That's 1 WIMP interaction per century. These are really rare events. Now, contrast that if I just took a kilogram of detector material and put it in one of the labs here, you would see from environmental sources of particles, you would see of order 100 hertz of signals. Compared to what we're sensitive to now is of order 1 event per century. Okay, so that's a signal to noise of 10 to the minus 12. So that's a big hurdle. If you want to try to look for this stuff, how do you deal with this? That's not really a pretty number to face if you're trying to propose an experiment. So, well, one thing is, okay, some of these signals are coming from cosmic rays. This is basically radiation from space. This stuff hits the upper atmosphere, produces a shower of particles, and what makes it down are these things called muons, which are basically a heavy version of an electron. Well, let's just get rid of that. So people realized early on that, well, I can go underground, I can go to a standard industrial mine, okay, and that blocks a lot of the cosmic rays. So these are all underground labs. Many of them are mines, or were mines. It's a function of their depth in a weird unit called meters water equivalent, which means if I had water, how much would it be absorbing? And this is the log of the muon flux. So here we are at the surface. The rate of muons at the surface is about 1 per 100 square centimeters. 100 square centimeters is about the size of my palm per second. And we get a reduction of about a factor of 10 to the minus 6, 10 to the minus 7 in that rate by going to some place like here, Homestake. That's actually the lab where Harry and I have done and work. So this is nice because there's a lot of facilities that already exist for us to use to get rid of these cosmic rays. Another thing to think about is that, well, I mentioned that we want to look for nuclear recoils because that's what WIMPs would primarily produce. The backgrounds, the noise, is primarily caused by gamma rays from environmental radioactivity or electrons. These things would primarily interact with the electrons of the material. So I'm looking for something like this that's kicking a nucleus, and most of the signals in my detector are kicking electrons. So if I can build a detector that can distinguish this from this, nuclear recoils from electronic recoils, I can remove a lot of my background. So it's not a problem. So the way that people do this is that when a particle comes into a particle detector and deposits energy, that energy will be distributed into several channels. Some of that will go into charge. It will rip electrons off the atoms in that material. Some of those electrons will fall down back onto their atoms and produce photons. We call it scintillation light. Some of the energy will go into just vibrating the atoms in the crystal, photons. So the thing is that the recoil type, whether it's a nuclear recoil or an electronic recoil, will be manifest in how that energy is distributed among these channels. So I'll just not to go through them, but there's some experiments. Here's ones that look at both charge and scintillation. Here's ones that look at both scintillation and vibration, etc. CDMS, that's Harry mentioned that in the beginning. Here's one of those germanium detectors he mentioned. It's about the size of a hockey puck. They measure ionization, charge, and also vibration, phonons. And this is from one of the detectors. When they calibrate that with gamma rays, they see this band here. If they put in neutrons will hit nuclei, they produce nuclear recoils. They see this band here. So they're able to distinguish if an event shows up in this band, that was an electronic recoil, that's background. If it shows in this band, it's a nuclear recoil. It's potentially a signal. All right, so let's go back here. Now let's try to sort of make sense of those three different epochs that I talked about. Well, each of these epochs has an innovation that epoch used. So in this epoch at the beginning, they realized right off the bat that they needed to go underground to minimize the background rates. After a while, they realized that's not enough. Not only do we need to go underground, we also need to do discrimination between nuclear recoils and electronic recoils. And then finally, this last epoch used detectors that are scalable. Now, what do I mean by that? Well, most of these background particles that are producing signals in the detector are coming from outside of the detector. Okay? So I would expect that if I have a detector and I've got background, that most of those interactions will be concentrated towards the outside and fewer towards the inside. So if I have a very small detector, maybe those interactions are sort of distributed uniformly. But as I get to bigger and bigger detectors, I might get to a size where I've opened up a very low background, almost background-free region in the center of those detectors. Basically, the outside regions of the detector are shielding the inside regions. Now, I can only do this if I have a technology that I can scale up in size, or I can build a really big single monolithic detector. I can't take small detectors and build many of them to make up the same mass. It's just not going to work. I need to have one detector that I can build large in size. Now, that hockey puck, the germanium hockey puck technology, that's not scalable. Maybe I can build a little bit bigger crystal, but I can't make a well-behaved germanium crystal the size of a barrel, for example, and instrument that and read particles that way. It's just we don't have the technology for that. But I can take that barrel and fill it with a liquid that is a particle detector, and I can make that a bigger barrel and fill it with more liquid. Okay. So what people realized was that the way to scale up in size to take advantage of this third innovation was to use liquid detectors. And the liquid that has sort of stood out and has driven this final stage that really beats Moore's law in sensitivity is liquid xenon. So it's a kind of an interesting design of a detector. So this is the type of thing, this is that barrel I was talking about. You'd fill it most of the way with liquid xenon. You also have some gas xenon in there. Because there's both gas and liquid, we call it a dual phase TPC, which means time projection chamber, and that'll make sense in a minute. Okay. So a particle would come in, deposit energy. Okay. That liberates some electrons and it produces some scintillation photons as electrons fall back down at the interaction site. These photons propagate, and we have photon detectors called photomultiplier tubes, you may have heard of those, around the detector that can collect these photons, and tell how many photons are emitted. After that happens, we have an electric field here, so the electrons slowly drift upwards, and then we pull them out of the liquid into the gas, and in the gas they can reach some higher energies and excite atoms in the gas, producing more scintillation photons. This seems like a complicated way of measuring scintillation and ionization, but the point is that this method of measuring, of counting how many electrons came out of the interaction is very sensitive to small ionization signals, the kinds that we might see in a limb search. We can actually see ionization signals as small as single electrons. You can see single electrons popping off the liquid surface here with this technique. And because we're measuring two different channels, the scintillation that was emitted down here and the ionization, that allows us to distinguish between signal and background. So this is an experiment that when Harry was talking earlier, when he switched from this germanium hockey pucks type to liquid xenon, this is the experiment that he joined. It's called the Large Underground Xenon Experiment. Creative name, LUX. And later on, I joined this. This is about 1/2 meter in diameter and about 1/2 meter tall. This is, so it is a cylinder. You're looking upwards, basically taking the bottom off and looking up into the detector. These are these photomultiplier tubes. These are sensitive to single photons. It has 122 of them, 61 on top, and then the other 62 were on the bottom that was removed to look up in here. This white stuff is Teflon. It's very reflective to the scintillation light that xenon emits. Now we want to shield this thing from sources of background radiation, so this gets put inside a large water tank that was actually designed a lot by Dean White, who's an engineer here, and Suzanne Kira, who's I couldn't find a photo of. I wanted to put that in there.
Yeah.
She helped design as well. So that's the detector closed up. This all gets filled with ultra pure water. And
All
then-
that white stuff she did.
Oh, okay.
All
the
the white
tie-back.
stuff is Suzanne's.
Okay. And the stuff above here. That you
Yeah,
can
that's
see.
right.
And then once this thing goes in the water tank, we lower the whole water tank underground. No, I'm joking. Actually, we disassemble it underground. So it goes underground in a lab in South Dakota. It's about a mile underground. This is like a mile length here, and there's a cavern here that was excavated a long time ago. This is where neutrinos coming from the sun were first detected that proved to us that the sun is powered by nuclear processes. So this blocks out the cosmic rays. So this is a sense of the type of thing we would see. So each black dot represents an event, something where we saw a particle come in and deposit energy. And we measure the scintillation, and we measure the ionization. And these blue contours represent roughly where we would expect to see, and we know based on calibrations, electronic recoils, backgrounds. And the red bands sort of tell us where we would expect to see nuclear recoils or WIMPs. And we have pretty precise models for how the backgrounds here should be distributed. So these things here and here are not really, they're sort of consistent with statistical fluctuations around here. And actually, when we did this analysis, which was about a year, not quite a year of data, there was a lot of people on the team, and we had to do a statistical analysis, and two people actually from Santa Barbara, two grad students, played a big role in doing the statistical analysis. Scott Hauserschwart here, and Dr. Kurt Naircorn, who just graduated, played a big role in this. And then this is, to give you some sense of context, this it's maybe hard to see, this blob here is a region that's been sort of favored by supersymmetric models of supersymmetry. And remember I was talking earlier about the thermal, there's a range of possible thermal dark matter candidates, things that could be produced thermally in the early universe, went up to 100 TeV, that's 10 to the 5 GeV, that's there. So we are able to sort of probe up to the high energy, the high mass region of that. But it went down to much further, but I'll come back to that. So what I wanted to point out is that this was the most sensitive dark matter experiment at the time. We had some interesting press response. So some were sort of stoic. The Guardian said, this latest results in dark matter. Symmetry magazine was a bit more positive. Flux maps where dark matter isn't. We didn't see anything. The Telegraph was maybe a little bit more pessimistic. Dark matter, more loose than heather. Scientists admit detector has failed to find mystery particle. And then my favorite is the Sun. Super sensitive, 7 million pound Lux dark matter experiments, finds nothing. Very costly, fails to solve one of the This is how it gets picked up in the press. So, one more thing before we move on and change gears. After Lux, we disassembled the Lux experiment. We're now constructing a larger version to push our sensitivity further. It's called LZ. It's a merger of Lux and another similar experiment that was based in the UK called Zeppelin.